Well, we've been talking about how the band bending in the semiconductor, or the surface potential, affects the charge in the semiconductor. But it's the gate voltage that produces the surface potential, or allows us to change the surface potential. This lecture is about the relation between the gate voltage and the surface potential of the semiconductor. So here's an energy band diagram, and we're going to add up the voltages with Kirchhoff's voltage law. So the potential in the bulk of the semiconductor, deep inside the semiconductor, is 0. The potential at the surface is psi sub s, that's our surface potential. So the voltage drop across the semiconductor is the surface potential. There's also a voltage drop across the oxide, the delta V ox here. We add the two, and that's the voltage on the gate. Volt drop in the semiconductor is the surface potential. Volt drop in the oxide is the electric field in the oxide times the thickness of the oxide. Well, we can relate the electric field in the oxide to the charge in the semiconductor through Gauss's law. Say a little bit more about that next. But you'll recall that this charge, Q sub s, this is the charge in coulombs per square centimeter in the semiconductor. So let's take a look at that. Here's a p-type semiconductor. Let's say the surface potential is negative, so it attracts the positive holes and they accumulate at the semiconductor surface. So we know the field lines are going to point away from the positive charges. Gauss's law tells us that the displacement field in the oxide, dOx, is minus the charge in the semiconductor, because the charge is positive holes accumulating, but the displacement field is pointing in the minus x direction. Now, when we deplete or invert the semiconductor, we have a positive surface potential. We have negative charges in the semiconductor due to the ionized acceptors in the depletion layer, and also due to the mobile electrons, the inversion layer, if we're above threshold. So the charge in the semiconductor is the sum of those two charges, Q sub d, the depletion charge, and Q sub n, the mobile electron charge. So that charge is negative. The displacement field points from the positive charges on this gate here, not shown, towards the negative charge. And it's just minus Q sub s. Q sub s is negative, so the displacement field is pointing in the positive x direction. So that's Gauss's law, and that allows us to relate the electric field in the oxide to the charge in the semiconductor. Okay, now we can get back to relating the gate voltage to the surface potential. Okay, we have Gauss's law. From that, we deduce the electric field in the oxide. We multiply by the thickness of the oxide, Tox, and we have the voltage drop across the oxide. We recognize that the dielectric constant of the oxide divided by the thickness of the oxide has the units of capacitance per unit area, per square centimeter or whatever, farads per square centimeter. So we put this all together and we have our relation. Vg prime is equal to minus the charge in the semiconductor, whatever it is, accumulated holes, depleted dopants, inversion layer electrons, minus the charge in the semiconductor, divided by the oxide capacitance per square centimeter, plus the volt drop in the semiconductor, which is the surface potential. That's an important relation. We're going to be using that throughout the rest of the course. I'll remind you, Vg prime, this is just to remind us we're talking about an ideal structure, a structure in which when we apply Vg prime equals 0, the semiconductor is under flat band conditions. All right, so we've discussed before how the surface potential is related to the charge in the semiconductor. Now we know how to deduce the gate voltage that produced that surface potential. We have a simple relation that does that for us. So given a surface potential, we can determine the charge in coulombs per square centimeter in the semiconductor, and then we can determine the gate voltage that produced that surface potential. So if we were to plot surface potential versus gate voltage and do it accurately, we would get a plot that looks like this. For low gate voltages below threshold, there is a substantial change of the surface potential with gate voltage. Not a one-to-one change. The slope is a little less than 1, but we can manipulate the band bending in the semiconductor with the gate voltage fairly easily. Now, if we go to above threshold, large gate voltages, we find that it's much more difficult to bend the bands. The boundary between those two regions is a band bending of 2 psi b. That's when inversion begins. And then our question is, what gate voltage inverts the semiconductor? What gate voltage produces a surface potential of 2 psi b? Well, that gate voltage is going to be our threshold voltage, so it's an important voltage to know. So that voltage we'll call VT prime. Again, it's our ideal structure where everything lines up at 0 volts on the gate. VT prime is equal to minus the charge in the semiconductor when the surface potential is at 2 psi b, plus the surface potential, which is 2 psi b at this critical point. Well, the charge in the semiconductor is both depletion charge, ionized acceptors for a p-type semiconductor, ionized donors if we were talking about an n-type semiconductor, and the charge due to the mobile electrons. Well, at the onset of inversion, when we've bent the bands by 2 psi b, we'll assume that we still have a negligible amount of electrons in the semiconductor, mobile electrons at the oxide-silicon interface, and that most of that semiconductor charge is just depletion charge. So in that case, we have a simple expression for the gate voltage at the onset of inversion. That's our threshold voltage. The depletion charge is just given by our depletion layer theory with a surface potential of 2 psi b, and we have an expression for the threshold voltage. Right, that's an important number to know for a MOSFET, so we know how to compute it now based on the doping density and oxide thickness and important parameters like that. Let's do a quick example. Let's say our p-type semiconductor is doped at 10 to the 18th per cubic centimeter. We have some numbers for the dielectric constant of the oxide and of the silicon. You know, a reasonably thick layer of SiO2, 2 nanometers. And if we compute psi b, we'll find that psi b is 0.48 volts for this doping. 2 psi b is 0.96 volts. We can compute then, using depletion layer theory, the width of the depletion layer. It's 35 nanometers. Then we can easily compute the charge per square centimeter. In coulombs per square centimeter in the depletion layer, it's just minus Q times Na times the width of the depletion layer, and that's minus 5.7 times 10 to the minus 7th coulombs per square centimeter. We know the oxide capacitance because we know the oxide thickness and its dielectric constant. So we can put that all together and compute the threshold voltage for this MOS system, and we find that it is 1.3 volts. It takes 1.3 volts on the gate to bend the bands by 2 psi b and invert the semiconductor, and now we're at threshold. So we've done that calculation. I'll point out that this is a rather large number. Typically this would be a threshold voltage that's too large for us to use under reasonable conditions in most of the circuits that we're interested in. That's because we have not accounted for non-ideal effects like the semiconductor work function difference. We're still talking about this ideal system that we call VG prime or VT prime. We'll discuss that in the next lecture. Okay, so in depletion, we have the surface potential as a strong function of the gate voltage. This occurs when the band bending, when psi s is greater than 0 but less than 2 psi b. So we could ask ourselves a question, if we're interested in what gate voltage does it take to produce a surface potential of 0.5 volt, we can figure that out. Before we do that, let me just remark something we're going to discuss here in a minute. Our basic parallel plate capacitor, we have a capacitor with 2 metal plates separated by a distance. We have an insulator between those 2 plates. The thickness of the insulator is T sub INS. The dielectric constant of the insulator is epsilon sub INS. And if we compute the capacitance of this structure, the capacitance is dielectric constant of the insulator divided by the thickness of the insulator multiplied by the cross-sectional area of these plates coming out of the screen, and the units are farads. We'll normally be interested in capacitance per unit area, so just dielectric constant divided by thickness of the insulator. Now, what if we have two different insulators between these plates? Well, it's a relatively easy E&M statics problem to show that this is equivalent to two capacitors with these two different insulators, two capacitors in series. And the way we add two capacitors in series is by 1 over the total capacitance is 1 over the capacitance of the first capacitor plus 1 over the capacitance of the second capacitor. And each of these would be a parallel plate capacitor with a metal plate on each side, but it's equivalent to this structure. So we in fact have such a system here. We have a metal plate on the top. We have a dielectric, our gate insulator, maybe silicon dioxide. And then we have so there's our metal plate. There's our first insulator. And then we have a depletion layer in the silicon of a width WD. That's depleted of carriers. That's like a dielectric with a dielectric constant of silicon. And then deeper in the undepleted p-type semiconductor, that's a conductive layer that is almost metallic. So we have a metal plate on the bottom. So what we have here are two capacitors in series. The first one is due to the oxide, and the second one is due to the depletion layer in the semiconductor. Okay? All right. Now let's get back to the problem we're trying to solve. We want to know what gate voltage produces a surface potential of 0.5 volt in this example. Well, we could do it exactly. We just plug 0.5 volts into our expression and compute the gate voltage. There is another way to do it, which is going to be approximate, but is going to be very useful for the rest of the course. And that is to think about this system as though we have two capacitors in series. We apply the gate voltage on the top of the oxide capacitor. The surface of the semiconductor is right here, and we're interested in the surface potential for this given gate voltage. So this is just voltage division with two capacitors in series. Now, it's a little more complicated because this second capacitor is voltage dependent. It depends on the width of the depletion layer, which goes as the square root of the surface potential. That makes this problem a little more complicated, but if we ignore that voltage dependence and just take some average surface potential, then we have a very simple circuits problem. So let's do that. Let's say that the capacitance of the semiconductor is the depletion capacitance. We'll assume that it is not voltage dependent. We'll just use some average value for the surface potential. It doesn't vary strongly with surface potential, only as a square root, so we'll get close. And then we do voltage division. And this may be something you've seen in a beginning circuits course. The potential between the two capacitors is the potential applied at the first one, at the top, times the first capacitor divided by the sum of the two capacitors. That's just voltage division with two capacitors in series. So we can write that. What we find is that the voltage at the gate is some number n times the surface potential. This number n, m, is just the ratio of these capacitors, 1 plus the ratio of these two capacitors. So you can see it's always going to be greater than 1. In a well-designed structure, it'll just be a little bit greater than 1 in depletion. Okay, so we could use that simple way to answer our question. What gate voltage produces a 0.5 volt surface potential? Well, we have our parameters up here. It's going to be important to compute M. And we compute that from the depletion capacitance and from the oxide capacitance. We put numbers in, we'll get M is equal to about 1.2, a little bit bigger than 1. So in this particular example, the gate voltage that produced that surface potential of a half a volt is 1.23 times 0.5, 0.62 volts. If we apply 0.62 volts on the gate, we will get 0.5 volt surface potential because we've lost some voltage due to the volt drop in the oxide. All right, so with this simple capacitor model, we can do that calculation. Okay. So we've answered our question. A half a volt surface potential takes 0.62 volts on the gate. That's an approximate solution. We could also put numbers in and compute it exactly. We'd get a bit different answer, but this approximate way is so useful to use in practice because the parameter M can be extracted from the measured transistor characteristics easily, and then it can be empirically adjusted to fit to measured data, that it proves to be a very useful way to address this problem. Okay, now we've talked about what happens in depletion. If we apply a gate voltage that is above the threshold voltage, then we bend the bands by more than 2 psi B, but we find that it becomes harder and harder to continue to bend the bands. We can bend them a little bit more than 2 psi B, but not very much, no matter how big of a gate voltage we put on it. In this regime, above threshold, the change in surface potential with the change in gate voltage is very small. We bend the bands by about 2 psi B, and it's really hard to bend them much more. Okay, why is that? Well, that's because when we go above threshold, the charge in the semiconductor now is this depletion charge plus the inversion charge, which begins to increase exponentially and dominates. So that a small additional band bending in the semiconductor produces a very large increase in the charge in the semiconductor. What that does is to increase the voltage drop across the oxide. So most of that increase in gate voltage beyond the threshold voltage just increases the volt drop in the oxide, and very little of it increases the volt drop in the semiconductor. You could say that highly conductive layer, silicon inversion layer, screens out the electric field due to the gate, and not much happens in the semiconductor beyond the inversion layer. Okay, so we've done what we set out to do in this lecture, relate the gate voltage to the surface potential. So the gate voltage induces charges in the semiconductor and bends the bands. There is a simple, exact relation between the gate voltage and the surface potential. We've seen that. The gate voltage is the sum of the volt drop across the oxide and the potential drop across the semiconductor. There is also an approximate way to do this, thinking about this system as 2 capacitors in series. Then the surface potential is just some fraction of the gate voltage, and that's determined by this parameter M. We evaluate that by using some average value of surface potential when we evaluate the voltage-dependent depletion layer capacitance. And that is a widely used approximate technique for relating the gate voltage to the surface potential, and we will see that many times in the remainder of this course. All right, we're ready to move on to the next topic. We've written our gate voltage as VG prime. We've written our threshold voltage as VT prime. We've said that that refers to an ideal system where at 0 volts on the gate, the bands are flat. What are the non-idealities in practice that we need to account for? That's what we'll discuss in the next lecture.